bring it up if you haven't.
Well, how many different P's you get from Andrew for this?
Okay. All right, so we solved the particle in the box. What I want to talk about next, actually I got a little bit off the sequence I'd like, and I apologize, you had already a homework problem or two on it. But now I'd like to explain how we're going to go calculate things like momentum, average momentum, and average position from the wave function that we found. Okay. And let me introduce a little bit of a formalism. In fact, I kept sort of saying, wow, momentum is kind of this derivative of psi, and energy is sort of this derivative of psi, the wave function. There's a nice way to talk about this, and let me now do that. What we say is that instead of talking about, or in addition to talking about momentum in the normal way, we're going to think about operators. Okay? So what we'll say is that P hat equals h bar over I d by dx. This is the momentum operator. Okay? E hat is I h bar d by dt. That's the energy operator. X hat, well, that's just x. It's the position operator. And I don't think of these things sort of in isolation, right? So I don't think of the, well, I can think of them in isolation, momentum operator, but it isn't very useful. I mean, sometimes you want to prove some theorem or something and manipulate it, but what I want to do with it is what I want to do is if I want to find the average value of P, I'm just going to take this as a rule now. From now on, what I meant is do that. Take the complex conjugate of psi, then put the operator, then put psi, create this product, and then take the average, then take the integral. If psi was properly normalized, then that's the average. Right? The integral in some sense is the adding up, just like you would sum your test scores. Because I normalized psi, I divide it already by the number of students in a way, and that makes an average. And indeed, that's the average value of psi. But there's a language we like to use. We say that this is the expectation value. Of P, of the momentum. I mean, if you want, it is the average. But it's a slightly nicer language because it's kind of saying, look, the particle is represented by the wave, and I can ask a question like, what's its momentum? There's no deterministic answer, there's a probabilistic answer. The expectation value is the most likely answer, or the average answer, I guess is maybe a better way of saying it. Okay? So we call it the expectation value. And these are the various operators. Okay, there are more operators. I mean, I can have an operator which is, I can square one of these operators. I can have x hat squared, and then that's just x squared. Or I can have p hat squared, and I square that, right? If I wanted to find the kinetic energy, it would be p squared over 2m, where I have the operator. And I'm just telling you that the rule is you stick it in front of this wave function, you put the complex conjugate wave function over there. Okay, so let's apply it in this case. to the case of our, I'll leave that up for just a moment longer. But let me write here that for our particle in a box, psi was the square root of 2 over L sine n pi over Lx, right? And the energy sub n, and that's, I should put a sub n there, is pi squared h bar squared over 2mL n squared, right? So that's what I had. So what's the expectation value of x? And I'll write a sub n because the answers I'm going to get are going to depend on the n, the n of the state. So again, that's just write down x psi star, x hat, psi. But x hat is just x, and psi is this. So that's 2 over L from squaring that. X, I'll just write it down once. And this is sine squared n pi over L x dx. Now, in principle, of course, I integrate from minus infinity to infinity, but here psi is 0 outside of 0 to L. And as I discussed last time, whenever I see the sinusoid, either sine or cosine squared, I immediately turn it into this other form. Where sine squared is 1/2 of 1 minus cosine of 2, 2 whatever it was. If it's cosine squared, you just get a plus there. Okay? So x sub n, average, I'm not always going to do integrals out, but let's do this one out. Let's do it all. X, 1/2, 1 minus cosine, 2n pi over L dx, 0 to L. Okay, the half cancels the 2. I have 1 over L times this and then that. The integral, the 1 times the x, the integral of x dx is just 1/2 x squared, running from 0 to L, evaluated at 0 to L. And then there's a minus sign of x cosine 2n pi over Lx dx from 0 to L. And squeeze in my final bracket there. This is just 1/2 L squared, obviously, right? For this, I'm going to have to integrate by parts. Your book gives you several formulas for integrals. Kind of cleverly, they give you all the integrals you need for almost all the homework. But look, at this level, you should be, don't rely too much on that. Some of these integrals are kind of ugly and not very much fun. But this integral we should just do, right? X times cosine, how am I going to attack that? Integration by parts. This is u, because I want it to go away. I want to take a derivative of it, and that's dv. If you remember, integral by parts is that the integral of u dv is uv minus the integral of v du, right? So now that's 1/2 L squared. Well, let me continue to write it with the big bracket outside. That's 1/2 L squared minus, okay, so u times v is x times the integral of cosine is sine, and I take out the interior and flip it over. Integrate that, evaluate that at 0 and L. Minus, now I had this minus sign, so it becomes plus. the integral of v and du. Now du makes x go to dx. I had all of this as u, so there's a constant out front. Okay, let's look at this term. X and L is just L, but sine of all this at L is just sine of 2n pi. That's 0. And 0 is times x there, so that is a big 0. This term's also 0. You could probably see that if I integrate cosine, I'm going to get sine. I'll get this L over 2n pi thing squared. Oh, by the way, there's a minus sign here. Not that it matters because the whole thing is 0. If I integrate sine, I get negative cosine because the derivative of cosine is negative sine. But if I integrate cosine, I'm going to get sine. Sine evaluated at these two boundaries with this L in the denominator, it's going to be sine of some number of 2 pi's. So that's clearly 0 at both at 0 and L, right? Do it yourself if you need to be convinced. So the whole answer is, those are both 0, and it's 1/2 L. The expectation value of x is 1/2 L. And that didn't matter what n was. And that actually is consistent with the, let me turn this instead of a drawing of the energy of the potential, let's sketch in the wave functions. Remember, they look like that, etc. But if you remember when I squared those to make the probability, I ended up with that. And when I squared this one, I ended up with a 3-hump thing. The average is always the middle. They're not asymmetric. They're symmetric about the center. Even if there's, what's a little bit interesting is this second one has 0 probability of the particle being at the center, but it's equally probable to be over here as over here. So its average position is the middle. And that's not a weird quantum thing. I mean, it is weird that a particle does that, but that, as a mathematical fact, that's just a feature of the average hump of a camel is in the middle where there is no hump of a 2-hump camel, right? There's nothing quantum mechanical in that statement. Okay. Fine, so that was x. So let me go ahead and erase this. Let's look at P. The expectation value of P is psi star P hat psi dx, integrated over all space, which is 2 over L, integral of sine n pi over L times x. Now, p hat operator was h bar over I. And then d by dx, and I'll go ahead and take the derivative of sine. I get out n pi over L times cosine n pi over L x dx. Okay? Which is h bar over I two n pi over L squared, integral of sine of n pi over L x times cosine of n pi over L x dx. There's a trig. This is cosine of something times sine of something. There's a trig fact that sine A cosine A is a half sine of 2A. Okay? So this is h bar over I n pi over L squared, integral of sine squared. No, not sine squared. Sine 2n pi over L x dx, 0 to L. Now I could do this integral. I'm going to stop here and argue that this is 0. right? If I integrate sine, I get cosine. Cosine isn't necessarily going to be 0, but I'm evaluating at 0 and L, and the argument has 2 times n pi. So if I evaluate it at L, cosine will be 2n pi, which is always 1, no matter what value of n is. So that it's the same, it's 0 on the L, and it's 0. Now, so the average value, the expectation value of the momentum is 0. So that makes sense for 2 reasons. One is a slightly nitpicky technical reason, but it's not. Don't ignore it. This will save you on an exam. The momentum operator has this I in it. Okay? When I got to this point, I had this integral to evaluate, which I didn't evaluate, I just argued through. But nonetheless, I had to do this. I had h bar over I, and this is all real. The integral had to be real. There's no complex bit in there. This had to end up being 0, because otherwise I would have gotten an answer which had an I in it. Got to dot my I's. And it's a theorem that I won't prove, but it's a fact. There's a theorem that you would prove if you take the next level of quantum mechanics, that it's built into the structure of what we've done, that you're not going to come up with complex numbers for the observable things like energy, momentum, position. And it's just always going to be magic. The moment that if you end up with an I there, then the integral is going to be 0. And so if you're working through a problem and you're finding that the momentum is some imaginary number, then you've made a mistake. Your integral should have been 0. If this thing was an exponential, then there would have been an I coming out of the exponential when I took the derivative, okay? So, remember a plane wave, I do get a value of momentum which isn't 0, okay? It's not just momentum that's going to do that. Could work either way. And the other thing, of course, is this is a particle confined to a box. So is its average momentum, can it be non-zero? No, because that would mean it was moving either the left or right on average. If it's in the box, it has some energy. Its momentum ought not to be 0 in some sense, but its average momentum ought to be 0 because it can't be moving left or right. It's stuck, okay? So that actually brings us to the next thing we'd like to look at, which is the dispersion. Dispersion, is another word for sigma. The variation in x and the variation in p. Sigma x, sigma p. And of course, Heisenberg uncertainty says that the product ought to be h bar over 2 or bigger. Sigma x squared, let me write it just the square down. Just to be clear about it, that ought to be, take the x hat operator, square it, and do that. That's essentially x squared average minus psi star x hat x dx. That's average x squared. We already found that. That's 1/2 L squared. So I don't need to do that integral. And this integral is just psi star. The x operator is x, squaring it times psi. So this is simply 2 over L, integral x squared sine n pi over L x dx. And then I have that. In this construction, I have that, and I have a sine squared. So I've got to do this integral, x squared sine squared. Okay? As should come as no surprise, I would take 1/2 of 1 minus cosine 2n pi over L x for the sine squared. And then I've got to do the integral of, going from 0 to L, I've got to do that integral. Right? That's that term. There's a term there, etc. I'm not going to work this out. It's in the front of the book. Well, there's a term here, x squared times 1. That's a trivial integral. It's 1/2 x cubed. I'm sorry, besides the 1/2, integral of x squared is 1/3 x cubed, evaluated at 0 and L. The integral of x squared times cosine, I'm going to integrate by parts twice. I did show you that often when I do these integrals, that these things vanish because of boundary conditions. but it's not guaranteed. And in fact, there are terms that don't vanish when you do this out to the gory end. All right? And so if you do that integral, and I could easily imagine putting this on an exam, for instance, although I'd probably have given you a number of integrals, one of which was this integral, if it was on an exam. Sorry, I don't have it memorized. When I work this out, the first term, integral of x squared, gives me x cubed. And that amounts to 1/3 L cubed. And the second part is, sorry, L cubed, but there was an L there, so I get an L squared. And the second part is minus L squared over 2 pi squared n squared. So the whole thing is L squared times 1/3 minus 1 over 2 pi n squared. Fine, that's what it is. There's nothing intrinsically interesting in it, but that's what it is. It's this. Okay? It's that's the average sort of width of the how dispersed it is. Okay? Note, and usually in quantum mechanical systems, in fact, I think almost always, in fact, it is always, when you have a quantum system with like an n, if you take n off to infinity, in some way you will recover sort of the classical result. The classical result is that sort of an average, the particle in something like that, it doesn't have some sort of uncertainty as to where it is. It's not always obvious how that classical result relates to the quantum system, but in this case, if n goes to infinity, well, this term goes away, okay? Although I still have, in this case, okay, I'm sorry, this was a bad example. In this case, sigma x still has this finite value. The point I wanted to make simply was that taking n to infinity is typically a way to look at the classical analog. All right, so that's sigma sub x. Sigma sub p, I'll write it down with a square. So it's psi star p hat squared. So the expectation value of p squared minus the expectation value of p quantity squared. We already found that, that's 0. So this is simply, I'm going to write everything down. The size give me, again, a factor of 2 over L from taking the 2 of them. This one is sine n pi over L x. Now, p squared is h bar over I squared. And then 2 derivatives of the sine. That brings out the coefficient of x twice. If I take derivative of sine twice, I get a negative sign. Right? Derivative of sine is cosine, derivative of cosine is negative sine. And then I get back sine here, the sine, the function. All right? So that's easy enough. That's straightforward enough. That's an h bar. Once again, sine squared is 1/2 of 1 minus cosine of 2 n pi over Lx. If I integrate that cosine, not only is it the same on both ends, it's a sine and it's a 0. So this part, I only have to worry about the 1/2, basically the 1/2 times dx just becomes an integral of 0 to L. So all of this is minus 2 over L times 1/2 L. That's the result of doing this integral. H bar squared over I squared is a minus sign. And then this is n squared pi squared over L squared. Those things cancel. So sigma p, that was sigma p squared. And all of that cancels. It was h bar squared n squared pi squared over L squared. This is h bar pi n over L. All right? If I look at sigma x for n equals 1, if I plug in n equals 1 here, I have 1/3 minus 1 over 2 pi. That turns out to be 0.181 times L. Okay? Let me write n equals 1 here. And sigma p is pi over L times h bar. And so sigma p times sigma x is L's cancel. It's 0.181 times pi times h bar. And if you pop out your calculator and multiply pi, which is 3 times 0.181, that's essentially, well, it is exactly 0.57 h bar. Okay? Which is a little bit bigger than h bar over 2. Just a little bit. It's a little bit bigger. All right? So it worked. I've calculated through, I found the sigma of the momentum, and it's nearly the value I expected as the minimum from the Heisenberg uncertainty principle. Okay? The value of sigma p times sigma x. What does it mean that sigma p is not 0?
That there are multiple possible momenta?
Not really. Not that there are multiple possible momenta. Anyone else? What does sigma p not being 0?
Is it a range of momenta? Not necessarily discrete ones, but kind of spread across.
Well, wait a minute. Yeah, okay. What you said maybe is not correct. I mean, it is correct in a way, maybe. It just wasn't what I wanted to get at. What happens when p averages 0, but sigma p is not 0? For sort of anything, what is that telling you? The p being 0 on average tells me that the particle is stuck in the box and doesn't on average move. But just again, like if, if I have anything, if I have any old thing as a function of x and I plot it and it looks like that, it could easily be that the average value is 0. But that's just missing the point that for many possible outcomes, x is not 0. And so simply I'm trying to say if sigma p is not 0, it's telling me that the thing does have momentum, but just that the average value is 0. I mean, it's really saying nothing other than, and it's consistent with what we know, the quantum mechanical fact is that you can't put a particle in a box and have it have 0 energy. You put the particle in the box, it has energy. The lowest energy state is this one. Perhaps I didn't mention it, but if you think a second, if I'd taken n equals 0, I get a solution to everything, but it was trivial. Psi was 0, because I had the sign of n pi over L. That's 0. Okay, so there's no real n equals 0 state. The first state is n equals 1. So this is a new thing. This is in quantum mechanics. What I don't have in classical mechanics is that I can't put a particle in a box and have it just sit there. It actually moves. On average, it doesn't go anywhere. But on average, sigma p is not 0. You know, there is momentum, and in the classical view of looking at it is that it's sort of sloshing back and forth. Basically, the particles maybe, racing back and forth like that, okay? Although what really is going on at a quantum mechanical level, you see as much as I do from just staring at these equations. That's sort of as much as we know about the particle, okay? But you certainly had the notion classically that if it has some energy, it has some momentum. Average momentum 0. Dispersion, we call this, or standard deviation of momentum, non-zero. Okay? You guys seem a little bit dead. It's Friday afternoon. And okay, you need to be able to work problems like this. I mean, I already gave you a problem or so for your homework, and you need to, you know, these calculations are fairly straightforward. At times a bit tedious, but again, the book gives you answers for the integrals, and so you should just be able to work them. All right. And that's what we mean in quantum mechanics to ask a question. What is the momentum? That's how you answer the question. Okay? You find the expectation value, which is an average. But what I want to mention now is that it's nice to avoid all these tedious calculations, right? I mean, all these integrals of sine and cosine. I don't enjoy it any more than you. Sometimes you just got to do it. There is a situation that often arises where you can avoid all of this. That's the notion, suppose I have Q. This is some operator. I might mean momentum here, I might mean energy, I might mean x. Imagine that Q hat times psi is a number times psi. Okay? And the number I call lambda. Now, I don't mean like if lambda is like x. X times psi, if x is, you know, the operator, x operator, then I get, sorry, I can write x hat times psi is x times psi. I didn't really affect it in the way that, you know, p hat, I've got to take this, I've got to take a derivative of psi. Okay? X hat is not that complicated, but still, that is a variable. I don't mean that. I mean if that's a number. Okay? Let me give you an example. If psi is my plane wave, and p hat is h bar over I d by dx, then p hat times psi is, take the derivative here. It's I times k comes down. Oh, and I can put a constant out front. I times k comes out, multiplies by h bar over I. This is simply h bar k times psi. And that is equal to lambda times psi, where lambda is equal to h bar k. Okay, so that's an example where I apply the operator to a wave function, and even though I took a derivative, I get back a number times the wave function. If this happens, we call lambda an eigenvalue. And we call psi an eigenfunction. And in particular, it's not just an eigenfunction in some general way. I always talk about it related to an operator. So lambda is an eigenvalue of the operator Q, and psi is an eigenfunction of the operator Q. You've probably heard these terms before. Okay? And if that's the case, everything is simple, right? If that's the case, then the expectation value for Q is psi star Q hat psi integral dx. And Q on psi is just going to give me lambda. And psi star psi integrated over dx, well, my normalization condition is 1. And so it's just lambda. Okay? So I don't have to do any integral. I mean, I write down the integral, but then I immediately see that the integral was trivial. It was just 1 by the way I constructed psi. All right? So that's really nice. Another feature is, what is sigma sub q? Let's go ahead and square it. Sigma q squared is integral of psi star q hat squared psi minus, I'll write it down, psi star q hat psi dx squared. I know what that is. This is just lambda squared. But I know what this is. If I do q hat times psi, it's q hat squared times psi is q times q times psi. So whatever it was, it's q. Let me just write this here. Q squared hat on psi is q hat on lambda psi. The q hat passes right past the lambda, so it's lambda squared on psi, right? I probably didn't even have to write it out. So this is also just lambda squared. And so this total is, these two cancel and it's 0. So if a wave function is an eigenstate of an operator, there's no variation in it. There's no dispersion is the language in that operator. Okay? And so the example that springs to mind is, again, the plane wave and momentum. If psi is a plane wave, I'll even forget the time part, then sigma p is 0. P average is h bar k, the sort of classical result. And the Heisenberg uncertainty principle told me that sigma x ought to go to infinity, right? That's what the Heisenberg uncertainty principle should say. And indeed, if I have that and I try to look, let me ask the question, for instance, what's x average? It's, e to the ikx, the x operator, x hat, which is just x. I take the complex conjugate there. These things just cancel. This is the integral. And by God, I got to integrate over the full wave function, which is from minus infinity to infinity of x dx. That's 1/2 x squared evaluated at minus infinity, infinity. Well, okay, I could maybe say that that's infinity squared minus infinity squared, but it's basically nonsense. Okay? If I look at the squared thing, basically there's mathematical nonsense. And we knew that. The wave function is, infinite in extent. And that's what we said initially, right? So a better language, a nice language for describing this is, I've got a plane wave with one value of k, then the particle is in an eigenfunction of momentum. It's an eigenfunction of momentum. It has an eigenvalue h bar k. Okay? And in fact, and we're not going to do this, when you study quantum mechanics at a higher level, it's nice to avoid all these nitpicky integrals and stuff. And there's many problems you can solve where you never actually do differential equations and whatnot. You spend your time messing with the formalism, and you can find the eigenfunctions of whatever you're asking about, the momentum or the energy. And then you never have to do anything messy, and you just calculate the answer right away. Although finding the eigenfunctions is not trivial. That's your whole job. So instead of the job of solving to find psi from the Schrodinger's equation, you just what the task is to find the wave function that's an eigenfunction of whatever variable you're interested in. And you just look at the whole thing that way. Okay, it's just a different way of working the problem. But often you can just guess it, obviously, as in the case of the plane wave and momentum. And sorry, I had one other thing I wanted to say about this. What was it? Oh, right. So was the particle in a box an eigenfunction? What do you think? Was it an eigenfunction of anything? What are the things that it might be an eigenfunction of? Call them out. Position, momentum, energy. All right. So is it an eigenfunction of position? psi equals a sine n pi over L x dx? No, it's not, because x operator times psi is x times psi. I mean, x is not affecting psi in the way that a derivative does, but this is not, I mean, for instance, I mean, that's not a number, that's the point, and that's the end of the story. But just to make it more explicit, if I ask what's the average, i.e. what's the expectation value, it's 2 over L, and I have to do this darned integral I did before. Okay? And that's the whole integral. And if it were an eigenfunction, this thing would have just come outside of the integral. Okay? So it's not. So it's not an eigenfunction of x hat, x. By the way, eigenfunction is it's a German word, and it sort of means sort of like self, like sort of self in a way. My German is too poor to do an exact translation, right? But the idea is, of course, you operate in something with it's an eigenfunction, you get back the thing again. Momentum, similarly, clearly not. So p hat times psi, I get a cosine, right? That's not the psi again. So it's not an eigenfunction of psi. But is it an eigenfunction of energy? Anyone? Well, remember, I split off the energy and time parts, but the full thing, now I use capital psi, was a sine, I'm sorry, we know a, it's 2 over L square root, n pi over L x e to the minus I e sub n over h bar t, where e sub n was n squared pi squared over 2m L squared. Oh, and I need an h bar squared. Okay? So if I ask about energy eigenfunction, I'm asking, is E of capital psi, which is I h bar t by dt of psi, what is that? And of course, the time derivative totally ignores the space part and just pulls down minus I h bar. So indeed, with an en, right? I just pull down these coefficients of t. And not only, so h bar cancels and I squared is minus 1 times minus 1. It is just en t. Yeah, sorry, en times capital psi. So yes, the expectation value of the wave function psi sub n is E sub n times psi sub n. Okay, writing this as psi sub n. Right? And I wrote it out very, very carefully, right? But it's just really nice. If you have an eigenfunction, things just fall out. You don't have to do any algebra. A final little comment here is, as I can construct a wave function, suppose I constructed a wave function psi equals psi 1 plus psi 2. I just literally take psi 1 with some coefficient, maybe I could put a constant out front, but I'll take this with n equals 1, and then I'll add to it with n equals 2. This value of psi solves Schrodinger's equation. Right? Because this will solve Schrodinger's equation, and that will solve Schrodinger's equation. Okay, so the combination, just think how it'll work out. I'll have on the left and the right, I'll just come back with the same thing. But it's not an eigenfunction of energy, right? It combines a state that has one energy and a state that has energy equal for state 1 and a state that has, that's state 2 that has different energy. And I can construct a system where maybe that represents 2 particles or something. We'll talk about how to do that later. But it's not the case that, all wave functions will be constructed this way, will be eigenfunctions of energy. You can imagine a superposition of 2 energies. It won't have definite energy. Okay. So any questions about that so far? Oh, it's Friday. So let's stop, and we'll do finite square well starting Monday.